Can you all hear me? Yes. Okay, we have a lot going on today. Oh, it's over here. Okay, so I have a lot of talking to do, but I do want to say that none of my slides are written by GPT or generative model yet. My slides today are still written by a human, but I don't know about next year. The field is progressing so rapidly. So let's get started. So I want to talk a little bit about the PyTorch roadmap, where we're going. So we have the 1.13.1 patch release landing on December 15th. I think the RC goes out next week. And then I want to talk about 1.14 that we've been working on. One of the key things that has been top of mind for us for a couple of years now is performance. And the reason it has been top of mind for us a lot is because GPUs are getting faster and faster, and they're getting faster in a way that we are not able to keep up with eager mode. So like the compute flops on GPUs are getting much faster, and the memory bandwidth is not getting as much faster. And there's like, with PyTorch, with eager mode, despite all of our best efforts in moving a bunch of overhead to C++ and reducing it, we're still not where we want to be. And that's been top of mind for us for a while, and we've been working on various projects to try to get to a better place. And as a consequence of thinking about performance over the last few years, we moved a lot of PyTorch from Python into C++, where PyTorch is basically a C++ code base. And that's like, I hate contributing to the C++ parts because you have to set up your build system and all of that. And at some point, we also, apart from realizing performance, we want to like bring back PyTorch or parts of PyTorch into Python itself. So we set ourselves a plan of, hey, how do we get to 30% faster PyTorch with no change to your model, unlike TorchScript and stuff? And how do you make it easier to write PyTorch backends? Right now, PyTorch has like 2,000 plus operators. And then how do you get to state-of-the-art distributed? We are doing a pretty good job, but like distributed is one of the most growing areas in AI. How do you scale up to larger models and stuff? And lastly, how do you bring PyTorch, or like most parts of PyTorch, back into Python? Well, this is what we set ourselves as a goal, and we were trying to think about how to actually execute on them. And so the route, like even going into more granular, like what we set ourselves as, how do you measure that 30%? Because I can say, we got 30%, and you can believe me or not believe me, right? So like, we set ourselves more granular benchmarks. Hugging Face transformers, like some of the top models in there, another 61 models from Tim, which is state-of-the-art vision models, and Torchbench, which we curated ourselves by taking papers with code and taking all the top tasks in papers with code. So you get a diversity of tasks, what kind of tasks are done within like the ML space. And then for each task, we take like the top PyTorch implemented GitHub repo and make it into a small wrapped benchmark without ever touching the code itself. So we thought this was a good proxy for measuring ourselves and whether we're actually getting 30% speedups or not. And we want to support dynamic shapes, and that's something that is generally hard to do for a deep learning compiler, but we're like, that's non-negotiable. Our users use dynamic shapes all the time, and by dynamic shapes, I mean you can change the shape of the input you're passing into your model without having it recompile. And lastly, distributed, we want all of this to just work, like it has to be 30% in the distributed setting. And obviously, it has to be robustness to correctness and accuracy. So we've been thinking about this a lot, and we're like, OK, cool. So what's the problem? OK, let's get started. Now, one of the things I want to break the problem down into is we know how to solve this, and this slide is actually from 5 years ago. Adam Pashka and I made this slide 5 years ago where we were like, oh, we know how to make PyTorch faster, build a compiler and do kernel fusion and out-of-order execution and stuff like that. And what I mean is just like a small, like you wrap your model in a torch.compile or something like that, and then you get a faster model. Now, the challenge has been building such a thing without compromising flexibility. And I think that's like the, that's like you don't want PyTorch to get crappier in order to get performance. You just want to get performance while keeping PyTorch like the same. So now, like, how do we think about these problems? First, let me break it down. So you have some piece of code. I call the first stage of building a compiler graph acquisition. How, can you actually like acquire that piece of Python code that you wrote reliably into our own graph format? And then the second stage called graph lowering, where you break that graph down into more fundamental, smaller pieces. And then the last one I call graph compilation, which is you actually then map it onto your big GPU or XPU cluster. So within this setting, you could, like let's talk about the first one, graph acquisition. How do you capture PyTorch graphs written in Python with dynamic shapes and stuff without compromising user experience? And that's a big challenge. And actually, like, we spent 5 years working on it. And like if you see, like, we actually built like 3 or 4 projects working on it, like torch JIT trace. It was just silently wrong if the if you invalidated the trace assumptions. JIT script, where you actually had to modify the code so much that people were like, it takes me 2 months to modify my code to be compatible with torch script. FX tracer, I think we never fully released it publicly. Lazy Tensor and Dynamo is something, 2 projects we were working on in the last year to try to do new approaches. Lazy Tensor and Dynamo did similar things, but Dynamo was a better technical approach, so I'll just focus on that for this talk. So they work, Dynamo works out of the box as is, but to the compiler, it gives partial graphs. So what do I mean? You take a piece of code, Dynamo identifies blocks that can be compiled and cannot be compiled. And then it passes the blocks that can be compiled to the backend compiler, and the pieces that it cannot be compiled, it just like runs with regular eager mode. And the way it does it is pretty cool, like nerding out a bit over here. It actually like hooks into Python, into the frame evaluation API, which was introduced in Python 3.7. And it actually reads the bytecode and identifies traces of bytecode that it actually can compile. And then it just patches that, the original code to shortcut to our compiled version if our guard assumptions are true. And Peng and Jason Ansel will talk about it later today in more depth. I just couldn't help myself giving a bit more of the detail. I think it's pretty cool. So we've been validating it, and we actually scraped like a bunch of GitHub projects, and then we ran Dynamo with them, and these are PyTorch projects. And Dynamo just works like 99% of the time on acquiring the graph correctly across like these 7,000 plus projects we scrape. And as of today, it supports 3.8, 3.9, and 3.10 of Python, and 3.11 support will come soon. So with Dynamo, we actually felt like we finally found a very reliable solution that reflects the flexibility of PyTorch and acquires the graph without having the user go through too much pain. We've been quite happy about building this. And that's something that I'll talk about more about how we try to push it into the release. And you can ask, oh, what about the gradients? OK, like get the graph. Like how do you like backprop it? And so what we did was we kind of used our Torch autograd engine in like a clever way. I wouldn't call it hacky, but like definitely very, very clever, where we overloaded it. We just like we look at what is happening if you run the graph in eager mode, and then we kind of just acquire it, and then we lift it back. Is in an ahead of time mode, and we call this ahead of time autograd or AOT autograd. So the graph acquisition and backwards, that's all settled. And then coming to backend, right? So the writing, like PyTorch has 2,000 plus operators today, and it looks something like this. It's like they're legit, but half of them are overloads, and like honestly, it's like 1,200 plus operators, and then like with a bunch of overloads, become 2,000 or so. And if you write a backend or a feature like VMAP or PyTorch, you have to like support this many operators, and that's like untenable. So we've been thinking about how to make it easier for contributors, hardware vendors to write backends for PyTorch. And the idea here is we want to reduce this 2,000 operators, decompose these 2,000 operators into a smaller operator set, and we want to call this like primitive offset. And so users write PyTorch as usual, and then it's our job in the backend to decompose them to a smaller primitive set. And we haven't settled on like how many primitive sets and what kind, but like that's something that we're thinking about. And lastly, I want to talk about the compiler. So on the backend itself, like with Dynamo actually acquiring the graph and then lowering to 810 prim IR, you can actually give it to a bunch of compilers, but we actually thought about building our own Torch native compiler called TorchInductor, and it's heavily powered by OpenAI's Triton project. TorchInductor is, we have a bigger deep dive later today, but it's actually written, it's a compiler that's written all in Python, and I think that's awesome because I can like hack on it pretty easily. And it's breadth first. It tries to cover as much of PyTorch as possible rather than saying, oh, it only works for like these small sets of models. It works on CPUs via using GCC and LLVM, and for NVIDIA GPUs, it works with Triton as our backend. And it doesn't work with Volta and anything except Volta and Ampere GPUs. So the older NVIDIA GPUs don't work. It also doesn't support other GPUs. So CPU support is being worked upon very closely by Intel. Intel has been a great partner, have been sending a lot of contributions to this backend. And for other GPUs, AMD is actively working on support. And there's some effort to try to like backport Triton to also work until Pascal GPUs, but anything before that, it's unlikely we'll see any benefits. So Triton, just briefly, is like a DSL written in Python. It's like a CUDA, but you can write like at a higher level and in Python. And so TorchInductor uses this like low-level DSL to actually generate sophisticated code automatically. So you as a user don't have to do anything. The TorchInductor's job is to do the compilation. And then we have a few other backends, and a few other backends in the works as well. So I will introduce all the pieces of technology that we want to deliver in 1.14 and beyond. And let me come back to this slide, right? This was the plan to actually deliver 30% performance across multiple precisions, across amp precision, which is like float 16, which generally gives higher speedups, and float 32, which is already doing a reasonably good job within PyTorch, so you're not going to expect as much more. And we basically took these like sets of 161 or 163 models and talked we were figuring out how to get these speedups. So where we are today. On float 32 precision, as of today, we get 24% speedups on TIM, 45% on TorchBench, and 22% on Hugging Face. Out of the box. Like you just like wrap your model, and then it just works. And on amp precision, this gets way crazier. Like we start getting real numbers that a compiler should see. We see 42% increase in TIM models, 86% on TorchBench, and 62% on Hugging Face. And really, consequentially, that means if your model training is running for 5 days, now it runs like 62% off. No, it's 60% faster than 5 days. It's like 3 days or something. So I think that's like real meaningful change in your productivity with this kind of stuff. And like the way we could do an aggregated speed up is like 75% of AMP and 25% of float 32. And that's something we established when we started this effort. It's not something we did post hoc. And we kind of are roughly looking at like reasonably good speed ups. Now, caveat. These speedups are on A100 GPU. If you try it on a desktop GPU like an NVIDIA 3090, the speedups are going to be slightly lower. And that's just that the faster and bigger the GPU, the more eager mode cannot keep up, and we need to introduce a compiler. So if you're using a GPU that's not that doesn't have as much like where PyTorch is already doing a reasonably good job, then like you're not going to see as much. But like I think they're lower, but they're still pretty good. So with all this, we were all pretty confident that this was a solid mode, and we are actually introducing today torch.compile within the PyTorch framework. And it is available in the nightlies today. And that's something that we want to ship into 1.14. And we have a few modes. We have a mode for smaller models. Like if you just have a tiny model and it's mostly framework overhead bound, we have a mode to like purely reduce overhead, but it trades off some other things. Like it takes a little bit of extra memory, but if it's a small enough model, you don't care. And then we have a mode that takes very long time to compile, but it will give you slightly better performance. And the default mode tries to just sweet spot everything. It takes about like 10 to 30 seconds to compile on average, and it doesn't take extra memory, and it kind of gives reasonably good speedups. Now, we have a few backends, but like Inductor is our default backend, as I said. And we support dynamic shapes, but dynamic shape support is very early. It is not yet ready for like consumption, but like when we actually do a stable release, it will be. But just one cool, my slides are here. One cool graph is we actually validated it with, say, GPT-2 training, and it does look pretty impressive. It's the thing in pink. And you can compare it with a commonly used trick in the industry called static shapes as padding, where, if you have dynamic sequence lengths, you just like statically pad them. And like dynamic shapes by natively will actually make a meaningful difference in performance versus doing static shapes and padding. And Horace actually will talk later today in more detail about this. And then lastly, we have full graph mode. By full graph mode, we mean you either compile the model as one single whole graph, or you give an error message. This is like a more traditional compiler. And that's kind of useful for certain backends, like, say, TensorRT, who don't like partial graphs and stuff like that. So the way you think about it, we're going to have eager, which is the default, but you don't get a bunch of performance benefits. And then torch.compile by default will emit partial graphs, and you'll get most of the benefits, except for like a little bit, like you can't export it to mobile, and like you can do some very advanced distributed parallelism. And then you have torch.compile with full graph mode, which might involve you changing your code a little bit, but it can give you that last mile 5% performance, or you can export it to various edge devices and things like that. So in some near future, and Michael Suo is going to talk about it, we will have a torch export of your model so that you can actually export it and send it out to a different backend completely. And in some far-flung future, we will have torch.compile not just wrap the model, but also wrap the entire training loop so that you can get more fusions across like you can fuse the optimizer in and things like that. So distributed works, and not only does it work, it has great speedups. These are AMP speedups with distributed data parallel. And you see some models are like, I don't know, 15% faster. Some models are like 80% faster, kind of. So if you make the model faster, the communication starts becoming more of a bottleneck. So at some point, we got to figure out how to like carefully adjust that as well. But the other interesting thing is actually like if you use FSDP distributed mode and you train any of these models, like because of the fusions and like carefully like managing and reusing memory, it takes lesser memory. So like so the TIM's vision transformer large, it's taking 70% of memory compared to eager mode. So you can actually fit a larger model in the compiled mode in certain settings like these. So that's kind of cool. And even in the compiled mode in non-distributed, that's something that we expect to an extent, though it's not fully true today. So the compiler that we built, it has a solid set of debug tooling, or at least like an early solid set of debug tooling. We have a minifier that actually, like, if you have an issue and you want to report it and you have a big code base, you invoke the minifier. It will reduce your problem to a small code snippet that you can post on GitHub and things like that. Just to summarize, we are introducing torch.compile in 1.14, and on our original goal of optimizing these 163 models, it worked out of the box without any change 93% of the time. And it works 43% faster on average in the aggregated numbers, performance numbers, compared to eager mode on an A100. So, OK, first, this is a lot of new stuff to take, and the room is like, OK, like I'm overloaded. Like, can you like calm down? So let me just like step back and say this is all going to land in 1.14. It's available in our nightlies today. And we're pretty excited about that. But then one of the things I was thinking is like how actually like the way users are going to use PyTorch is going to fundamentally start changing. Like they're going to use eager mode for most things by default and experiment and stuff. But anytime they start doing a large training run, they would want to switch to compiled mode and wrap their model in the torch.compile. And this is meaningfully new experience. It's not in terms of you using PyTorch, it's not going to be the same way as before in some deep way. And I think we have a road to showing substantial speedups, and we have our initial numbers today. So I was like, why don't we just call it 2.0? I mean, it makes sense. Like, we should just call it PyTorch 2.0, and we also can stop having those long version numbers for a little bit. And so we are going to actually call this 2.0. And within the 2 series within the 2 series of releases, we have a bunch of stuff planned around performance and compilation and scalability. We have some quotes from people who have tried this. First from Sylvain, who's a primary maintainer of Hugging Face Transformers, who tried it, and he, in his own words, he said, hey, I added 1 line of code, and it's like 1.5x to 2x faster in the models I trained. And that's like a good validation that it's not just us pretending to say that it works, and you have to believe in this room. Luca Antiga, who's also here, says nice things. I will let you read it for a sec. But basically, we've tried to validate it with some of our most power user PyTorch customers, and they seem to agree that this is a solid direction, and this is a nice thing that they would support for PyTorch to go into. Ross Whitman, who is a maintainer of TIM, also tried it, and he basically is like, it just works with majority of TIM models. I didn't really have to change any code or have that experience that I had with, say, TorchScript kind of thing. Now, what else, right? Okay, we're going to deliver 2.0 stable release in the beginning of March. And it's available in the nightly starting today, and you can go try it. And obviously, like, it's going to break in many million ways, and you're going to be like, oh, Soumith, like you said, it's going to work. So file away those GitHub issues. And in the rest of the 2.x series, we're going to release 2.0 stable early March. And in the rest of the 2.x series, we are working on, as I said, the stable primitives that I talked about, export mode, support for more accelerators and backends. And I think, and we know how we can get a lot more speedups than we have today. We have a bunch of ideas around compiler optimizations. And there's a bunch of ideas here, actually, that we want to do, but we don't have the bandwidth. And now that we built this entire compiler stack in Python, and it's easy to contribute to, even though it's conceptually it's a compiler and it's like hard as in general, we would love you to take part. Like, come help us build this thing. File a GitHub issue on what your plan is and what you plan to improve. We have, what's my next slide? Oh, yeah. We have a Q&A webinar happening over the next month or so where you can talk to the devs directly, maybe discuss some of the ideas you want to implement. So 2.0 is fully backward compatible by definition, and I want to say this out loud because people will say, oh, 2.0, does this mean I have to rewrite my code? Despite everything I said in the slides, I think that's easy to misunderstand. We didn't do a rewrite. Like, it's the same code base. It's the same code. It's just we're introducing a new substantial feature in compilation mode, and that's fully optional, and you wrap your model explicitly to get that mode. So your code base works as is. I mean, we were going to call it 1.14, and then we were like, oh, it would be nice to call it 2.0. So it's fully backward compatible. So before you go on Twitter and be like, is 2.0 fully backward compatible, or should I rewrite my code? I'm telling you up front. Try it today in the nightly binaries and give us feedback. And we have a bunch of deep dives starting from the next talk on how each of these technologies actually works under the hood. And don't miss our Ask the Engineers series that is starting this month online. And also we have some office hours if you want to try it out today in the afternoon and you have questions with, you can bring your laptop on. At the back, we're going to have the office hours later today. With that being said, I will start handing it off to Peng Wu, who will deep dive into Torch Dynamo.